we'll now discuss on the shear and moment diagrams for a beam. This is a continuation of what we had discussed last or in the previous video, and this concerns the drawing of the shear and moment diagrams in order for us to determine the variation of the shear magnitudes as well as the moment magnitudes as our basis later on in design as to where we are going to reinforce more, especially for concrete materials, or even for steel and other materials for the beam. So it will guide us in placing our splices also for the reinforcements, and all stresses governing the design of beams would be essentially based from the variation of shear along the span of the beam. So in the book Behavior, because I think all of you has already a copy of the book Behavior, chapter 4, particularly in section 4.3, it discusses how the derivation of the value of shear as well as moment in the general beam loaded with different types of loading, like concentrated loads plus a uniform load, or maybe uniformly varying load. And it turns out that with the derivation, we have the equation that determines the shear, which the derivative of u with respect to x is equal to w times of x. This one is the slope of the shear diagram. The slope of the shear diagram and this is equal to the intensity of the distributed load. While dm over dx, the derivative of the moment, is equal to b. And this is the slope of the moment diagram. This is just equal to the shear. And if we integrate these two equations, integrating this one with respect to x as well as moment, we will have delta v is equal to integral of w along x, or its magnitude to be measured distance x along the span where w is active. Or this simply means the shear, the difference in the shear v sub 2 minus v1 is equal to the area of the loading from 1 to 2. Which means that at any other point 2, the shear is just equal to V1 plus the area between points 1 and 2 of the moving diagram. The magnitude of W is to be added to V1 to obtain V sub 2. Or this simply is the change in shear and we have also delta moment is equal to the integral of v of x dx, which means that m2 minus m1 is equal to the area of the shear diagram from point 1 to point 2. So again, for moment, the moment at point 2 is just equal to the moment at point 1 plus the area in the shear diagram between points 1 and point 2. This just demonstrates the relationship between the load magnitude of the loading diagram to that of the shear, the magnitude of the shear or the shear diagram to determine the values of the moment along the span where the variation of the loading is covered by the 2 points 1 and 2. So it's just considering the variation of the loading between 2 points, in this case 1 and 2, and then corresponding to the shear area that will determine also our moments. Okay, let us demonstrate this one with an example problem so that we will clearly see how it is going to be done. Okay, so the beam is simply supported beam. Hinge at point A and then roller at point B, which makes the beam to be statically determinate. We have a concentrated load of 249 kilonewtons at point B, a uniform load of 30 kilonewtons per meter from point C to point E, which is 6 meters in span. And we have a moment counterclockwise acting at point C, which is 234 kilonewton meters. So just like what we did in our previous examples, before we can proceed to determining the shear and moment values at different points where there is a change in loading, like point A, point B, point C, point D, and point E, we have to solve first the reactions as basic requirement, because we will not be able to determine the variation of the shear and moment without knowing the reactions first. So at point A, we will have our reaction R sub A, and at point B, we will have R sub B. So initial moment point A equal to 0, we will have counterclockwise positive. This will be RD times the moment R. 3 times 3 is 9 meters. Then plus this moment, applied moment, because RD will have counterclockwise moment. So also it is given applied moment at point C. So this is plus 234 kilonewton meters, and minus 249 kilonewtons times its moment arm from point A, 3 meters, and also minus the moment of the uniform load. It will have a clockwise moment, 30 kilonewtons times the span of 6 meters times the moment arm, which is located at point T. T plus 3 plus 9 meters of 0. So R sub D plus 237. Of course, directed upward. Then we have submission moment at joint B of 0. We will have clockwise positive. R sub A times 9 meters minus 234 kilonewton meters. Also minus 249 kilonewtons times 6 meters. The uniform load of 30 will not have any movement as far as point is concerned, because the centroid of this uniform loading will have location that is simply located at point E. The moment arm is 0, so its movement will not have any effect on a moment summation at point B, meaning that its movement is also equal to 0. So this will be equal to 0. And R sub A 182 kilonewtons. We can check the accuracy. Checking, we have the sum of RA and R sub B should be equal to the total applied load. So this is RA plus R sub B. Is it equal to 249 plus 30 times 6. RA is 192 plus 237. Is it equal to 429? So we have 429 plus 429. Is it okay? It just confirms the accuracy of our reactions, and it maintains equilibrium of the beam along the vertical. There is no load along the horizontal, so it also indicates that it is stable. It is in equilibrium along the horizontal as well as along the vertical direction. So after we have the reactions, then we can start solving for the shear and moment values. We will first consider the shear values. joint A, if these are joint A, let's not exaggerate. This joint A. A little to the left, joint A, let's call it joint point 1. And then a little to the right, joint A is point 2. Because there are points at certain locations, especially with concentrated loads, that a single point will have two shear values. Okay. So our consideration is to imagine point A as the center of that particular point, and then a little to the left of point A, we can consider it as point 1, then a little to the right of point A is point 2. Because here, a little to the right of point A, a little to the left, I mean, we can call that one as BE1. And BE1, if you consider that R sub A is acting at the center, actually at point A, center of point A. This is our R sub A. So, a little to the left of point A, we call that as our B sub A, the shear point A, a little to the left, the point. And this is equal to 0 because there is no load. There is no load applied to the point, a little to the left of point A. And then, with this application of R sub A, upward forces are positive. A little to the left of point A, this is point 2, is equal to B sub A 1 plus R sub A. Or this is equal to 0 plus R sub A 182. Which means that B shear B sub A, which is equal to 192 kilonewtons. And that is positive because R sub A is going up. Okay, so we can define actually the 2 points or the two values of shear at point A. The starting value is 0 and then it goes up by the magnitude of R sub A. So this is how we picture out, we imagine the point once subjected with a concentrated load. There is two values of shear at that particular point. Then at joint B, if these are joint B, again this is point 1 of B, and then point 2, and we have the applied load, which is 249 kilonewtons, point B. So, a little to the left of point B, the shear is B sub B1, and it is referred from the value at B sub A2 with span which has no loading. Between A and B, there is no loading. Meaning, the shear at point A, a little to the left of, a little to the right of point A, will be brought to B sub B, or a little to the left of point B, B sub B1. And this value, B sub B1, will just take the value of B sub B sub A. and this is equal to 1 into kilonewtons, because there is no load between A and B. The shear a little to the right of A would just be equal to the shear a little to the left of point B. And then vis-a-vis 2 is equal to vis-a-vis 1 minus forces that are directed downward would be a negative, or will develop negative shear. So the 249 is downward, so we have a negative value for that in developing the shear. We have minus 249, which will give us vis-a-vis 1 is 192 minus 249, 192 minus 249 negative. As soon as we draw the shear and moment diagrams, our reference line, which is the zero horizontal line, below the horizontal line, below the reference line, all shear and moments are negative. Above the reference line, shear and moments will be positive. So once the value is negative, then that will remind us that that value is below the reference line. So joint B. Joint C, this is our joint C. This is point 1, point 2, joint C. And then joint C is the start of uniform load. Okay, this is 30 meters per meter. So B sub C a little to the left, because there is also no load acting on span BC, on the member BC. There is no load, so B sub C1 is just equal to B sub B2 plus 0. Now there is no load, or this is B sub B2 is negative 57 plus 0, or we maintain negative 57 kilonewtons. B sub C2, the uniform load of 30 kilonewtons per meter will start at this point, but we will not count that as an additional shear, because it's just the starting point of a uniform load. It's only on concentrated loads that we will consider the change at a single point, which makes that point to have two values. But in this case, since it is just the start of uniform loading, then B sub C2 is equal to PC1 plus 0, meaning there is no concentrated load at the center. So this is negative 57 plus 0, or we have negative 57, which means that BC1 and BC2 will just have one magnitude of the shear. It will just vary as soon as we go towards point B. Okay. At train B, we have the load. R sub B, which is equal to 237 kilonewtons. So shear at B, we take to the left, is equal to the shear at C2 minus 30 kilonewtons per meter times 3 meters. Again, the uniform loading is directly downward, so it is also negative, no? Or the shear that is developed by this uniform load will be negative. So all forces actually acting downward will develop a negative shear. So minus, and our V sub 2 is minus 57 and minus 90, which gives us negative 147 kilonewtons. This BB2 shear at the, a little to the right, is equal to shear at the 1. Then this force is, or this reaction is directed upward, so it's a positive shear of 227. This is 147 negative plus 237 gives us 90 kilonewtons. And then finally, we have the uniform load ends at point E, 30 kilonewtons per meter. This is point 1 and this is point 2. Shear at point E, looking to the left, is equal to the shear at point D, 2 minus 30 kilonewtons per meter times 3 meters. This gives us BB2 is 20 minus 90 equals 0. We have to take note that the shear diagram will start with 0 at the left support, or at the leftmost support, and it should end with 0 at the rightmost support. So we have at least partially has a value that will somehow confirm that the previous values of the shear diagram could be correct, because the shear at this point becomes 0, or we have a 0 value for the shear. That should verify the results of the previous values. And V sub E2 is equal to V sub E1 plus, see, there is no load, no? Or there is no concentrated load at the center of E. So there is no load, which is 0. So VE1 is 0 plus 0 equal to 0 also. Okay, and we will continue with the determination of moment values before we can finally draw the shear and moment diagrams. So we'll have our moment values. For moment, oftentimes when the variation of the loadings are just concentrated loads and uniformly distributed loads, or even varying uniformly varying loads, the moment at every change in loading, we just have a value which is 1. There's only one value, no? But in cases where there is an applied couple or an applied moment, then this is the case when we will have two values, which we will see here. At point A is equal to 0, because there is no load to the left of point A, and since the support is hinged, this could not simply carry any moment. No, there is no moment that is developed in a support that is a hinge support or a roller support. We can only develop moment when we have a fixed support or a fixed joint. So h sub A is 0. To solve for h sub B, This is equal to m sub A plus the shear at between A and B. We'll have to look at the shear, the variation of the shear diagram from point A and point B. And if you can recall, if you look at the computation for the shear at point B, they have the same value, no? Which is just equal to the reaction at point A, which is 192. Uniform, 192 kilonewtons. And M sub A is just M sub A is the value of M A plus the shear area from A to B. And since the area here of the shear is a rectangular area with a constant value of the shear of 192 kilonewtons, so M sub B therefore will be equal to 0 plus 192 times 3 meters. 576 kilonewton meters. There's only one because there is only one shear area. Between A and B, there is no couple that is applied. And then next is moment at C. At moment at C, at point C, there is also no load, or there is no load between B and C, but we have a couple acting on point C. So in this case, MC1 is equal to M sub B plus the area of the shear diagram from B to C. Okay, that's MC1. Because here we will be expecting two values because of the presence of a couple or of this applied moment. And then if we look at the previous computation for the shear at C, which is negative 57, that negative 57 starts from point B because the shear at point B, later to the right of point B, is also negative 57. So with BC1, BC2, so it is uniform shear equal to negative 57. So moment at B, 576 minus, or we can use the plus sign, but use the negative value of 57 then times 3 meters plus 405 kilonewton meters. So that's the value a little to the left of point C. And then because we have an applied moment, we'll have MC2 equal to MC1. This moment is negative because it is counterclockwise moment, as we look at the derivation of the relationship between loading, shear, and moment. Counterclockwise moments are negative, clockwise moments are positive. That is the common sign convention that we are using for beams. So MC1 will be subtracted by 234 kilonewton meters, or MC1 is 405 minus 234, 171. Okay, so at point C, a little to the left of point C, we'll have a moment of 405, while a little to the right, it reduces to 171. That is because it is reduced by this amount of 234, which is an applied moment. Then for moment at B, this is equal to MC2, and we have the shear BC2 is negative 57, BB1 is negative 147. Okay, so this is the variation of the shear. So the shear area is trapezoidal. A trapezoidal meaning it is from small value to a large value on a span of 3 meters. So here the moment is the shear is negative 7. At point B it is negative 147. So moment at D is moment at C2 minus the area of the trapezoidal negative shear, and this will be plus shear at from point C to point D. Okay. So from this equation we will have MD is equal to MC2 171 is positive, and plus this is minus 57 and minus 147 times 3 meters, and this is divided by 2. This is the area of the trapezoidal shear diagram, and this will give us meters at we have our M sub E is equal to M sub D plus the shear area between points P and D to E. The shear area from D to E is a positive shear area, 90 ang maximum with 0 at the free end. So this is equal to EB minus 135 plus triangular, no triangular area, 1/2 times 90 times 3 or 90 times 3 minus 150. Okay. It completes also our moment values, and it starts with 0 and ends with 0. That also indicates that our moment values as computed are correct at this point, because if you start with 0 for the moment diagram, it should also end with 0 at the right end, whether this is a support or a free end. So it closes, meaning the diagram closes both in shear and moment values. So as soon as all the values are now computed, then we will draw the shear and moment diagrams. So the shear diagram starts with 0 at point A, and then it goes up by the magnitude of B sub A. For B sub A is 192, and it is constant towards point B. Then minus 249, and the value here is negative 57. This is 192. And then we have load our negative shear with a distribution of 30 times 3 meters, and it gives us negative 149. minus 149 plus R sub D, which is 2, R sub D is 237. Then the shear will go up by, from here, goes up by 90. And then uniform load 30 times A is 0. We will place a diagonal or diagonal lines. We will fill up the different shear values of the diagonal lines, while the moving diagram will have vertical lines. Okay, so these values are the ones that we have already computed for shear, and then for moment, moving diagram starts also with 0 here, and then in sub B we have 576. 576. And then MC1 is 405. So we have here 405. And then it goes down with 171 because we have a couple. So 171 here. Then at point D, M sub D is negative 135. Negative 135. And then it goes back to 0 at point D. This is a 0 degree curve. Kanina yan, 0 degree. In moment diagrams, even if we have a straight line with a horizontal or diagonal, it is considered as a curve because lotus of different points connected by either a line, straight line, or a curved line. They are all considered as curves. And the degree of curvature as we go towards the next diagram will be increased by 1, meaning if it is 0 degree, here it will be first degree. Diagonal lines are first degree lines. Horizontal lines are 0 degree. This is name this as a line, and there will be no cause of confusion. 0 degree line. Mas generic sa connection of different points. But it's 0 degree. In the moving diagram, it will not be first degree. Okay. Then this is also a 0 degree line. So from B to C, it's connected by first degree, and then in this will go down, and then from 171 to 135, this is a first degree line. Therefore, here should be second degree. In the moment diagram, it becomes second degree because first degree plus 1, so second degree. In the moment diagram, that will define this segment of the beam. And the behavior of the shear is increasing, negatively increasing. So this area of the shear diagram is negatively increasing. The shear area is negatively increasing. So this behavior of the shear area becomes the behavior also of the slope of the line that connects point C to point D. So negatively increasing, it means that we have a line, a second degree line that will start with 0. No, 0 is horizontal, and then it increases negative. Negative slope is from left to right to upper left to lower right, while positive slope is from lower left to upper right. This is positive, while this one is negative. So the slope that will determine the line, the curve from this point towards this point will have a negatively increasing slope. Negative and then increasing. So an increasing negative slope is will start with 0. Naka-increase ang slope, but the direction is negative. In this case, this will have the slope is increasing, and the slope is negative. Will be different if you do it with the reverse direction. It will not reflect the correct behavior. And then from point D to point E, it is positively decreasing. So the slope is like this one, and it gradually increases. So gikan sa 0 slope, 0 horizontal, then maximum ang vertical. So maximum, gikan sa maximum diri pareho sa 0. And this will now be the video of the moment diagram from B to E. So we will cover this one with vertical lines to differentiate from our shear line. So inside the curve, or the curves from one segment to the other, are the two values of our shear and moment. So after we have drawn the moment diagram, it will also give us the behavior of the curvature or the deflection of the beam from one end to the other end. A positive moment area will have a bending downward. Concave face of the beam will be facing upward, and the convex face is downward. So, and then there is a point here where moment is 0. Corresponding to that point in the beam diagram, it's where the stress is 0. Here, the moment is 0, therefore the bending stress is 0. And that will also be the location of our point of reflection. So if we define the deflection curve, the deflection shape of the beam, then this is downward, and then the location of the 0 we will call this one as the inflection point. And this one is our elastic cord. And this completes the drawing of the shear diagram and moment diagram as well as the elastic cord. Elastic cord is very important because it will show us the location of the friction point, which that is the location also where we can make our splices in the design of reinforcing bars, or in steel sections. That could be the location where we can also make our connections with splices also. Because sometimes the span of the beam may not be, or meaning the span of the available material like steel reinforcement or steel sections. We have a commercial size, commercial length only 6 meters. Although we can order much longer lengths, but oftentimes if we purchase our materials from ordinary hardware, then the commercial length is only 6 meters. So if it's not sufficient for the whole span, then we have to splice or the distance that is required. In this case, like this 9 meters, and if we have only 6 meters, then our splice should be located more or less at the location of the inflection point, or proximate to that point where the movement is not quite large. No, pwede pa diya maka-splice. Otherwise, we have to arrange our reinforcement that the splicing will not fall, especially at the location of the maximum moment, because it is experiencing the largest stress. So we should not place our splices at this position. And this inflection point again is also where we can stop pouring of concrete beams. No? Sometimes we may be stopped by maybe heavy rains, or some phenomenon that the pouring may not be continued. So as much possible, we have to stop the pouring at the location of the inflection point. Because again, there is no stress. The fact that there is no moment. So delikado. Diha kamuundang or diha pagtumpay sa atong reinforcements. And this will now be used in our design. Okay. And this is all for. Okay. We will have another example in another video.